Welcome back everyone. In this lecture I will give the second proof using matrix coefficients. So, let us recall what we wanted to prove. So, here is the theorem. So, the set of irreducible characters, they form an orthonormal basis for this space of class functions. So, let us list all the set of irreducible characters by chi 1 etcetera chi s. So, this form an orthonormal basis for this space of class functions. So, here we are assuming that G is a finite group. So, that is important assumption. So, we wanted to prove that straight away that span of this chi i's, that is going to be equal to this the space of class functions. So, now note that so this space of class functions, so this is indeed a subspace of this C valued functions from G. So, here we already have this basis consisting of normalized matrix coefficients. So, let us recall what is that basis. The basis is given by the following normalized matrix coefficients of these irreducible representations. So, you have this sum of these d I square elements which are given as follows. So, these elements form an orthonormal basis for this C G. So, now if we start with some element f in this z of C G, then definitely f is going to be there in C G. So, that means we will be able to write down that f as a linear combination of this rho I j k. So, we just write it down explicitly and use the fact that f is a class function to derive that f can be written as sum of linear combination of characters. So, let us do this computation. So, write f as summation I j k C I j k rho I j k. So, here the C I j k, they are all complex numbers for all I j k. So, basically we have written f as linear combination of this. So, recall that f is a class function. So, in particularly f of g is equal to f of h g h inverse for all g h in g. So, this is there for us. So, we are going to use this. So, now if we actually try to use this, so let us evaluate. So, we want to prove that f is actually belongs to the span of chi i's. So, that means we want to prove that f of x for any given x in G can be written as linear combination of chi I of x for fixed coefficients. So, those coefficients are going to come from these coefficients. So, let us compute it very explicitly. So, fix x in G and then compute this f of x. So, that is going to be exactly equal to summation C I j k rho I j k f of x I j k. But now, what we are going to do? We are going to just use this property star. Okay, let us try to use that. So, to use star, what we do? We rewrite the same equation f of x as 1 divided by cardinality of g summation g in g f of g inverse x g. So, it is a since f is a constant function on given conjugacy class, this equation is true. So, now what we do, we just replace this using the equation that we had before using this. So, if you replace this, then what we get exactly f of x equal to 1 divided by the cardinality of g summation g in g summation I j k c I j k rho I j k of g inverse x g. Now, recall that. So, rho of g is what given by this matrix coefficients rho I j of g, and rho is actually a group homomorphism. So, that means this can be split into product of 3 maps. So, this is exactly equal to. So, we are only interested in the ijth coefficient. So, we can write it as follows. So, let us not rush. So, we can write it as 1 divided by the cardinality of g. So, maybe one can take that inside. So, now f of x equal to summation I j k runs, and you have this c I j k, which are the coefficients that we will keep it, and then we collect 1 divided by cardinality of g summation g in g. So, now instead of this, so we will be able to write these 3 operators, which are given by rho of g inverse k, rho of x, and then rho of g. So, note that rho is a group homomorphism. That is why this operator rho g inverse x g splits into rho of g inverse rho of x times rho of g. Now, this is nothing but ijth coefficient. So, the ijth coefficient of that is going to be ijth coefficient of this. So, basically we have this very big matrix, and then we take ijth entry of this entire matrix. So, this is the ijth entry. So, that means this f of x is going to be equal to summation I j k again, and then c I j k. So, whatever term that we see here, so this part you can see that. So, this part is exactly this rho k hashtag. So, rho k of x hashtag. So, recall that T hashtag was defined to be the average sum of this rho of g inverse T rho of g. So, because we are dealing with only one representation. So, that implies that this term that is there in this red box, that is exactly equal to this entire term is exactly equal to this. So, that means, so here we will have the summation c I j k and then rho k of x hashtag, and then we are actually looking at the ijth entry of this. But since this T hashtag, this is G invariant map. So, that means this map, this is also going to be G invariant. So, all G invariant maps from irreducible representation to itself is going to be scalar multiple of identity. So, by taking traces, we already know that what will be that scalar. So, then it is clear that the rho of x hashtag supposed to be exactly equal to trace of rho of x divided by the degree of rho times the identity on that operator on that representation space. So, if we use that, then we can easily see that the ijth coefficient of this is going to survive only whenever I equal to j, because this is just a scalar times identity. So, this is scalar times identity. So, that means all entries that are there in off diagonals, they are all 0. On the diagonal, this scalar will appear. So, only non-zero entries will be coming from this I equal to j. So, I equal to j coefficients survive. So, that would imply that f of x equal to summation I comma k c I I k, and then the coefficient of this matrix, which is ith entry, and ith entry is given by this term, this scalar, which is exactly trace of rho x, which is chi rho of x, and divided by the degree of rho. So, which is exactly here in this case dk. So, this can be replaced as chi rho kx, which is chi kx divided by dk. So, that means we can see that this f of x that we wanted to compute is exactly equal to summation c I I k, where I and k runs over, and then chi k of x divided by dk. So, if from here we can easily see that f is exactly equal to summation I k c I k divided by dk chi k, and of course, the coefficient of chi k is going to be. So, if you rewrite in terms of chi k, so then you can see that the coefficient of chi k is c I k divided by dk, where I runs from So, that is actually comes from here. So, up to dk. So, from this it is clear that f can be written as linear combination of the irreducible characters chi k. So, this is actually a straightforward calculation. So, that if you write f as linear combination of the matrix coefficients using the property that f is a class function. So, one will be able to rewrite that f as linear combination of characters. So, this is indeed a straightforward computation that proves that the set of irreducible characters they actually form an orthonormal basis for this the space of class function. So, from this one can immediately conclude that as an immediate corollary, the number of conjugacy classes of G, which is exactly the dimension, which is the dimension of this space of class functions. So, this is going to be exactly equal to the number of irreducible representations of G. So, this is of course inequivalent irreducibles. So, this is something we get it for free immediately. And again this also immediately gives us the another corollary for a characterization of finite abelian groups. So, if we start with a finite group, and then we can say that it is abelian if and only if. So, the number of conjugacy classes that is supposed to be equal to G, the cardinality of G. So, that means the number of irreducible representations of G up to isomorphism, that is exactly equal to the cardinality of G. So, the number of inequivalent irreducible representations of G is exactly given by the cardinality of G. So, these corollaries are immediate from the main theorem that we proved. So, now let us try to use this information in order to actually get complete list of irreducible characters of some smaller groups. So, as an first example, let us actually look at this cyclic group. So, if we take this Z modulo n Z, so these are the examples. So, we take G to be this Z modulo n Z. So, since G is abelian, the number of conjugacy classes is equal to the cardinality of G. So, we have exactly n number of inequivalent irreducible representations. So, n will be the number of inequivalent irreducible representations of this Z modulo n Z, and it is not hard to prove that these following representations which we constructed earlier, they are all inequivalent irreducible representations which are given by the maps rho k, which are the group homomorphisms from Z modulo n Z to this C star, where the generator 1 bar mapped to this element 2 pi I k divided by n. So, I will leave it to you to check that so these are actually inequivalent irreducible representations of Z modulo n Z for k runs from 0 to n minus 1. One can take it from 1 to n also, not a problem. So, these for this k from 0 to n minus 1, this row k, they form the set of inequivalent irreducible representations of this Z modulo n Z. Since they are all inequivalent irreducibles and we can have only n number of inequivalent irreducibles. So, these are all inequivalent irreducible representations of Z modulo n Z. So, this is something like immediate from the result that we have proved. And this is actually something easy to prove in this special case, but we have proved this strong result even for general finite groups. So, now you can take it as exercise and then verify directly that the regular representation of this Z modulo n Z is going to be direct sum of these irreducibles, and you can see that since all of them are one dimensional. So, we get explicitly that the regular representation of this Z modulo n Z is going to be exactly equal to this rho 1 plus etcetera plus rho k, sorry, rho n, or you can take it to be 0 to n, yeah, minus 1. So, verify for G modulo n Z, we have that the regular representation is just the direct sum of these things. So, do straightforward verification, give explicit isomorphism. So, give explicit isomorphisms. Okay, so let us see actually what one can do for other non-trivial groups. Maybe I will work it out for the symmetric group S3. So, later in a later part of the course actually we will discuss how to construct irreducible representations of general symmetric groups, but for time being let us only work with some smaller examples. Okay, so, it is clear that in order to actually understand finite dimensional representations, it is enough to understand irreducible representations, and that means it is enough to understand irreducible characters. And what one can do, one can actually explicitly record that data which is captured by these irreducible characters in a matrix. So, that is called this character matrix. So, let us actually define what it is. So, here what we do, we simply take the columns of this matrix indexed by this conjugacy classes and the rows of this matrix indexed by this irreducible characters. So, then the ijth entry is just recorded by the value of this chi I on Cj. So, it is clear that chi i's are class functions. So, it is enough to actually tell what is this chi I of Cj. So, we want to just record the entire data, what are all these chi 1 etcetera chi s, and that is what recorded in this character table. The character table is given by this matrix S by S matrix Xij. So, like I said, you write these conjugacy classes here and then characters here. So, then the ijth entry, so that is going to be chi ij, which is exactly equal to chi I of Cj. So, here is your jth column, which is given by Cj, and here is our ith row. And this matrix X, and this is called character table. So, the character table actually completely has the information about the values of the characters on each conjugacy classes. So, once we read the character table, that means we can read all the characters. So, that means we will be able to tell everything about the representations of that given group. Okay, so let me just compute it for S3. So, here is the computation. As an example, let us focus on S3. So, recall that S3 is nothing but symmetric group on 3 letters, and the conjugacy classes they are indeed given by these following elements. So, because there are only 2 cycles and 3 cycles are possible, and then the partition of 3, that is what going to give us the number of conjugacy classes. So, if we partition 3 into non-negative positive integers, then you can see that you can get this following partitions. So, you can partition into 1 plus 1 plus 1 and then 1 plus 2 and then 3. So, there are only 3 conjugacy classes that are possible in S3, and it is not difficult to prove that the following representatives are there. So, all 2 cycles will be conjugate and then all 3 cycles will be conjugate in S3, and these are all the only elements. So, either identity or 2 cycle or 3 cycles in S3. So, we have these conjugacy classes represented by this identity 1 2 and 1 2 3. So, these are the complete set of conjugacy classes in S3. So, later maybe when we deal with the general symmetric group, maybe I will actually make some observation about why this partition of n actually counts the number of conjugacy classes and so on. But in this case, maybe you can straight away verify that these are all the only conjugacy classes. So, now we already have these representations, which is the trivial representation from S3 to C star, which is given by you send all the elements to 1 for all G in G. So, this is one representation. The second representation again we can take it to be the sign representation. So, which is given by taking the sign of a permutation. So, you take an element in S3 and then send it to its sign. So, that is a group homomorphism and that defines one dimensional representation on S3. So, it is easy to check that these two are irreducible because both are one dimensional and they are inequivalent representation, that is also easy to check. So, that may be clear from the character table, maybe I will write it in a minute. And recall that we defined this following two dimensional representation some time back and that is given by the following maps. So, it is enough to give how the action is defined on the generators. On 1 2 it acts as -1 -1 0 1 this matrix and then 1 2 3. So, this acts as -1 -1 1 0 and we verified that this is indeed irreducible by proving that both this 1 2 and 1 2 3 action they have no common eigenvector. So, this is irreducible two dimensional representation. So, now if you think about it, so we have this D1 is 1 and then D2 is 1 and then this D3 is 1, all of them are D3 is 2, all of them are irreducible representations of S3, they are inequivalent, that is easy to verify. Now, using this equation, the cardinality of G equal to sum of di square, we get that 6 is equal to 1 plus 1 plus 2 square. Now, since these numbers actually 1 plus 1 plus 2 square exhaust 6, that immediately tells us that there are no more irreducible representations. But anyway, we also proved that number of conjugacy clauses will be the number of irreducible representations. So, that gives us that these three are the complete list of irreducible representations of S3. So, in particularly if you draw the character table, you can see that we get the following table. So, we denote chi 1 by this chi trivial and then the chi 2 is that signed representation and chi 3 by this chi of rho 3. So, here is and you have identity 1 2 and then 1 2 3 these classes. Now, from the sign representation you can see that all elements are mapped to 1. So, basically the values of the images are going to be the trace. So, that means we get exactly 1 1 1 here and for sign representation it is going to be sign of the given permutation and you can see that sign of identity is just 1 and sign of 1 2 which is 2 cycle is -1 and sign of 3 cycle it is just product of odd transposition. So, even transposition. So, it is exactly 1 and similarly if we go back to this representation we can see that identity is mapped to identity. So, the value of chi 3 of identity is 2 and chi 3 of 1 2 which is the trace of this matrix which is exactly -1 plus 1 which is 0. So, this is 0 and trace of this matrix which is -1 plus 0. So, that is exactly -1 and this is the character table of so this is the character table of S3. So, now maybe I will state some immediate corollary or easy thing to check. So, if we take the regular representation and it is not hard to see that. So, I will leave it as exercise. So, check when we take the regular representation of this S3. So, then the character of that is going to be given by this following table. So, you have E 1 2 1 2 3 and then if we take chi regular on identity, it is going to be regular representation is 3 dimensional. Sorry, regular representation is 6 dimensional. I am talking about the standard representation. So, if we take the standard representation, you can see that on identity it is 3 and then on 1 2 it is going to be 1 and then 0 on 1 2 3. So, basically standard representation just permutes the identity matrix, the columns of the identity matrix. So, for example, 1 2 what it does, it just permutes first and the second column. So, you have 0 1 0 and then 1 0 0 and then 0 0 1. So, the trace of this is exactly 1. So, that is what you get. And from this you can conclude that so maybe like I will leave it as exercise, decompose chi standard into irreducibles, sum of irreducibles. So, that can be easily done using now the table. So, similarly do this for chi regular as well. Chi regular the dimension will be 6, but we already know that how to do that, but maybe you can directly verify this by giving the isomorphism. Again decompose and verify using the table. Okay, I will stop here. So, this actually kind of completes the story about the character theory. So, I will actually start with some applications of representation theory in group theory and general algebraic number theory in next class.